So this review paper we are looking at goes through all the, many of the convectively coupled equatorial waves derived from observations. Deriving them from observations obviously requires some very smart filtering using the spectral features. So these are the boxes that the model uses, the filtering uses to look at the various waves. I'm just going to run through. The details in the paper are really important in terms of the similarities and differences between waves derived from observations in terms of their phase speeds, wavelengths, vertical structures, horizontal structures, reflections from the top of the or stratosphere back into the troposphere, and so on. I'm not going to go through all those details, but you can read them up. I just want to kind of run through these waves to see how the linearized systems give us most of the information for the horizontal and vertical structure of the waves and their propagation and so on, and we are left with some unexplained details like this equivalent depth and the propagation speeds and wavelengths versus equivalent depths, and the impact of the waves on the stability, and how the concepts like gross moist stability can be used to try to patch up some of the differences between wavelengths in the vertical and the equivalent depths we get from theory and so on, or the parameter equivalent depth we need to fit the observations to the model waves and so on. But just to look at them is important and interesting. So here we are looking at distribution of annual mean variance of the cloud top temperature TB that we had looked at before, filtered for the Kelvin wave, equatorial Raspy wave, tropical depressions which require a different kind of filtering, mixed Raspy gravity waves, and n equal to 0 eastward inertial-gravity waves and westward inertial-gravity wave bands. All are shown for preferred direction of propagation and preferred location of tropical cyclone genesis associated with each mode. So we have been looking at equatorial Kelvin waves, and several times I mentioned the dynamic boundary and the equator and the coast and so on, but you can see that it clearly drifts off the equator here in terms of the variance in the cloud top temperature, which gives us Kelvin wave signature, and the impacts on tropical cyclones is expected here. Tropical cyclogenesis is basically looking for a few things like vorticity, humidity, vertical velocities, vertical shear, ocean heat content, and so on. And you can't generally track the cyclone from its birth to the formation. Typically what we do is look at when the tropical depressions or cyclones are formed, and look at the frequencies and seasonality and say where are the regions of cyclogenesis and how they are related to phases of the waves and MJOs and other convective activities like mesoscale convective systems and so on and so forth. Okay, so the Doppler shifting of the waves in the atmosphere is very common. Air is a very light fluid and easily Doppler shifted. The waves are easily Doppler shifted in the atmosphere. In the ocean there is Doppler shifting, but since the ocean is much heavier and moves much more slowly, it's not so easy to see examples of strong Doppler shifts in the atmosphere, in the ocean. Okay, so here is the n equal 1 equatorial Raspy wave. You can see the off-equatorial peaks. There is westward preferred propagation. This is eastward preferred propagation, and there are impacts that are known in terms of tropical cyclogenesis. There are some that are potentially argued to be important, but you can see that the nice symmetric structure we see for the n equal equatorial Raspy wave in the linear models is not there. Here quite symmetric, but here not so symmetric. And this is the mixed Raspy gravity wave moving westward, preferentially affecting tropical cyclogenesis, or at least we have identified the regions where they happen. So There are other features like the monsoon trough that sits here, which is also favorable for tropical cyclogenesis. This is n equals 0 equatorial, eastward propagating inertiogravity wave, westward propagating inertiogravity waves, and you can see the variances, and the scales are not all the same here, so you have to be careful. The range is larger here than for the mixed Raspy gravity waves and inertiogravity waves. Okay, so that's the variance. You can also see the zonal distribution of the amplitudes of the variance, annual mean variance of cloud top temperatures associated with each of the waves. Looking at the time longitude section of the same thing, averaged between 2.5 south and 7.5 degree north from 1st April through 2nd June 1987. We can clearly see, so time is going down this way and longitude this way, so you see the signatures of the waves in the MJOs with our embedded superclusters that we talked about, propagating eastward, bending westward, and the 2-day waves that propagate westward and bend forward. So the whole multi-scale structure in each sector of the Pacific, Atlantic, and Indian Oceans are seen here. So some of them persist throughout. They are circumnavigating, but as we talked before, the convective phase tends to disappear in the colder waters over the East Pacific. This is maps of the same anomalous cloud top temperature, geopotential height in contours, wind in vectors, with a minus 20K perturbation in Kelvin wave TB at the base point of 7.5 north, 172.5 degree east. For day 0 at 850, day 12 at 850, day 0 at 200, and day yes, those are the three, the contour intervals and other details. So you can see the waveforms here, Kelvin wave at the top of the boundary layer, the phases and the associated convergence, divergence features again shifted away from the equator, more in the ITCZ, so there are interactions with the heat sources there. And this is on day 2, so you can clearly see the eastward propagation here and the disappearance of this phase as you get into the eastern Pacific here. And in the upper atmosphere, you expect the opposite feature, so you have convergence in the lower level and the divergence in the upper level, so you carefully can look at the geopotential height contours, but obviously the structure is much more complicated compared to in the simple linear solutions we looked at, and you can also see this upper tropospheric trough here appearing in the geopotential height in terms of the westerly duct and other features that we talked about that affect the Doppler shifting of the waves and change in the phase speeds, wave numbers, and so on. But gravity waves are non-dispersive. The Kelvin wave is not affected by these, mostly the Raspy waves. This is the time height sections of anomalies of zonal wind, temperature, and specific humidity at Majuro, or maybe Mahuro, I'm not sure how it's pronounced, at 7.1 degree north and 171.4 degree east. A scale to a minus 20K perturbation in Kelvin filtered TB at the nearest grid point on day 0. So this is looking at height versus time, so it's going back in lead and lag. So the temperature signal is shown here, and the pressure coordinate signatures in this is the, let me make sure, this is the zonal wind, this is the temperature in B, sorry, A is zonal wind, B is temperature, and C is specific humidity. Again, you can see the vertical propagation of the Kelvin wave related signature in zonal wind, temperatures, and humidity. And we talked about these tilting structures before, and we talked about this kind of a structure in the lower troposphere and the stratospheric signature here. So you can see that we are going from the surface into the stratosphere here. So the radiating boundary conditions and the rigid lid type of boundary conditions and the vertical propagations up and down of the waves and so on are inferred from this kind of filtered observations. But it's good to see many similarities in the observed waves compared to the linear models we looked at. Same thing here, maps of anomalous temperatures and geopotential height fields and wind vectors with the minus 20K perturbation for the westward inertial gravity wave at 850 hectopascal minus day minus 1, 0, and this is in the upper atmosphere. Just try to remember the basic features we talked about, the rotational versus divergence convergence features of the Raspy waves versus Kelvin and inertial gravity waves, and westward propagating inertial gravity waves versus eastward propagating inertial gravity waves, surface signatures versus the upper atmospheric signatures, which indicate the vertical structure, and the associated geopotential height perturbations that go with the waves, because there is always heating and vertical motion and geopotential height accelerations involved, as you remember from the equation. This is looking at the westward inertial gravity waves in zonal winds, temperatures, and humidity with the cloud top temperatures shown here. Again, you'll see the upper stratospheric features much more clear in the temperature in terms of the structures we talked about, and the signatures in the winds are centered here more in the lower stratosphere, and the humidity signature obviously is much stronger in the troposphere, which is what you expect. This is associated divergence and heating structure, Q1. So you can see where the heating is maximum, around 500 millibars or hectopascals. That's where the heating associated with the deep convection tend to happen, and there are associated divergences and convergences in the vertical that are very critical for the waves that we are talking about. I'm just highlighting some features to show that convectively coupled equatorial waves are real, and we are desperately trying to explain their vertical and horizontal structures and propagation speeds and wavelengths and so on and so forth. This is now using a empirical orthogonal function approach to extract 2 to 10 day westward filtered OLR and regressed 800 hectopascal winds. So the first empirical orthogonal function of westward filtered outgoing long wave radiation, which is indicator of convective activity as well, so moving waves like mesos, MJOs and mesos that we talked about. So the Raspy waves emanating from here, propagating into the Asian monsoon and Indian summer monsoon and the East Asian summer monsoon regions are shown, are associated with these kind of signatures. So this is looking at 30 north, 30 south over 1979 to 2006. Okay, what can we say? We have the familiar convergence, divergence patterns, and a lot of work is required to explain the tilting. Why do equatorial waves not just propagate eastward? Why do they get tilted northwestward? Background circulations matter. Typically when we did linear shallow water and linear atmospheric equations, we assume that background state is stationary, and you can add simplified idealized background states to look at Doppler shifts, but this is the real world. So obviously we try to use the processes we discussed before like the heating, the relation with the vorticity, the relation with the stretching, the relation with humidity, and so on, to explain the various observed features. Not always completely, but nonetheless. So this is the mixed Raspy gravity wave. Again, see the structure here now, quite different compared to the other waves we have been looking at. Oops, here, for example. So mixed Raspy gravity waves have the equatorial symmetric, asymmetric structures, depending on whether it's mode 1 or mode 2. Here it's day 0, day +1, and upper level, so lower level and upper level, and associated rotational features. So these are showing cloud top temperatures and stream functions and wind vectors associated with the same -20K perturbation for the mixed Raspy gravity waves. Hopefully you remember the spectral wave number frequency diagrams and remember the characteristic structures and propagation directions and speeds of each of these class of waves. Raspy waves, Kelvin waves are simpler, but mixed Raspy gravity waves and inertial gravity waves and so on. So this is showing the temperature and meridional winds at Majuro again, at 7.1 north, 170 east or so. And this is the temperature, mixed Raspy gravity waves, and this is the specific humidity. So this gives you a sense that moisture is a big part of the wave dynamics, which is used in the so-called moisture mode theories that we looked at for the MJOs, and whether the moisture is getting lifted with frictional convergence at the surface, or if it's happening associated with the weak temperature gradients and other observed dynamics in the atmosphere, in the free troposphere, and so on. We looked at and compared the various models, but in the waves it's not so easy to separate them just based on observations. This is what we this is why there's a chopper going by. This is why we build the models, and each model picks on different process as the dominant process, but you know that none of them explained completely all features of the MJOs, but mostly we were aiming at the planetary scales and the speeds of propagation being slower than the free waves. So let me not spend too much more time on this. This is n equals to 0 eastward inertial gravity waves. This is the time height section of the n equals 0 inertial gravity wave in zonal winds, meridional winds, temperatures, and specific humidity. This is the n equal 1 equatorial Raspy wave, again showing more of the rotational aspects of the Raspy wave. So background winds, zonal, meridional, and vertical shears, impacts on the phase speeds, changes in wave numbers. Short waves can, longer waves can get squeezed and become shorter waves and deposit energies by slowing down because of the Doppler shifting by the background winds, or they can get tilted northward away from the equator because of the background winds, and so on and so forth. This is the time height section of the n equal 1 equatorial Raspy wave, and that's it. So stare at them again and read the paper if you're interested in the details of each wave. Has an impact on the atmospheric processes which are critical, and we are always looking for those process understanding and whether and how the convective feedbacks and moisture feedbacks happen, and how the wave and the mean flow interactions happen, which way the energy propagates. All these things are important for process understanding because they're also important for predictions and predictive understanding. As we said, S2S predictions and so on do depend or try to exploit the predictability associated with these waves. Waves especially are important for prediction and predictability, because if the heat source is here and it sends off a wave, if there is a wave to track the wave, if there is a way to track the wave and look for its impact on temperature and precipitation elsewhere, obviously you have good way to increase your prediction skill. That's always the main goal in the end, but just understanding atmospheric circulation is of great interest as well. Okay.